Hello guys, thank you so much for being with me in another machine learning tutorial video. We talked about supervised learning in several videos. In this video I will explain about unsupervised learning. In this video I discuss clustering, and next I will examine another method in the field of unsupervised learning, which is called K-means algorithm. Unsupervised learning has other methods, for example reducing the dimension. In the next sessions we will talk about anomaly detection. I have also included information about recommender systems in the form of presentation files, and I will dedicate a short video to this concept too. In unsupervised learning, we are not given any information about the correct answer in the training set. The goal is to find the structure between the data. For example, a grouping. For example, these data are close to each other, so they are placed in a cluster, and how these clusters are interpreted is not related to the computer, and interpreting these clusters is our job. We have already mentioned the example of similar news categories. Clustering has many uses, as I have already explained. Another application of this discussion is in market segmentation. Here we have grouped unlabeled data. We have distinguished the clusters by colors. The first clustering algorithm is the K-means algorithm. Here is the two-dimensional figure actually. So even visually data can be clustered. We have randomly considered these triangles. As the centers of the clusters. We will introduce the best method to consider the initial center of clusters. From here on, two loops are formed. In the first loop, we check which of these points each data is closest to. We have already done this, and these are the demarcation were obtained in the same way. The data in the red border is closer to the point that was considered as the center of the red cluster, and we have repeated the same for the blue and the yellow clusters. If we have actually 3 clusters, we will have this. Okay. This is the second step in the K-means algorithm, and then we average all the data in each cluster. A new point is obtained. We consider this point as the new center of this cluster. In this way, we update the centers of each cluster. Now we have to check which data is closer to which center for all data. We continue this work until neither the centers change nor the cluster corresponding to each data. That is, this algorithm has two outputs. One is the center of the clusters, and the other indicates which data belongs to which cluster. I have put the implementations in Python files for you. We will also examine its problems. This algorithm is very widely used, but it is not the only clustering algorithm. Chi is the number of clusters that we value ourselves. In our classification problems, we always add the feature as a bias factor. No need to add this x0 here in the implementation code snippet. The mu's are the centers of the clusters. We said that we had two repeating loops. We calculated the Euclidean distance between each data with all co-centers, and we considered the smallest distance as the criterion of belonging of that data to the cluster related to that center. The loop is very simple and the implementations are also very simple. If you are familiar with Python, understanding these codes is very easy for you. Indexing of clusters starts from 0, similar to other indexing in Python. As we said before, axis is equal to 1 means performing calculations in a row, and axis is equal to 0 means performing calculations in a column. If these square bracket CI's actually do not change, the algorithm stops. So the algorithm is very simple, its implementation is also very simple. But until now, every problem we had, we defined an objective function and solved the problem by minimizing it. We want to do the same thing here. Each data belongs to a cluster. We store these clusters in the vector Ci. We want this data to be as close to the cluster center as possible. That is, we want to reduce the dispersion of clusters. So here we can determine the objective function in the same way. In fact, this means algorithm did the same thing. To minimize our objective function, we must consider the centers as fixed and change the clusters in such a way that the distance between the data and the centers of the clusters is minimized. Once we consider the clusters as fixed and change the centers so that this distance is minimized, in practice we should do the same. This objective function has a minimum. It has a global minimum point. Do we necessarily choose the global minimum solution? One of the problems of the Cummings algorithm is that depending on the initial random points we choose, we may not reach the global minimum solution. Of course, it is not necessary to get the global minimum answer. We said that the final answer is very dependent on the initial choice of cluster centers. As we said, we choose these points randomly. What do you think could be the problem here? Here, no data belongs to the yellow cluster. Because it is placed behind blue. Here, actually. Green, yellow, I don't know. A cluster may remain empty. So this method is not a very good method. Instead of randomly selecting the initial points from the entire space, we randomly select the initial centers of the clusters from the data itself. In this way, we are sure that each cluster has at least one data. It means that no cluster remains without data. We use the permutation command to randomly move the rows of the X matrix. Then we remove a code to the first row. Coding in Python is so easy. Any complex command can be written in a single line of code. I have also used this method in the implementation of Python files. We said that reaching the optimal local optimum or global optimum solution is very dependent on the initial points. We have several methods to reach the global optimum. For example, we can perform the algorithm several times or more. Of course, in this case, we must be very careful because this algorithm is too slow for big data. For this reason, we can measure the runtime of the algorithm. For example, if it takes 2 minutes to run the algorithm and we don't have 10 more minutes, then we repeat this algorithm 5 times. Among all of these results, we choose the clustering that has the lowest cost. But there is still the problem of being time consuming. Another way is post-processing clusters. That is, after clustering, we change these clusters a little. For example, we divide each cluster into 2 clusters and again apply the Cummins algorithm to these smaller clusters and merge these clusters again. We need to do a sequence of dividing the clusters and merging them. In cases where n-dimensional data cannot be drawn easily, if we can make this data graphable in some way, we can understand clustering much more easily. One of the solutions is to reduce the dimensions. In this way, the clusters can be visualized, and now the minimum number of clusters is clearly 1. The maximum number of clusters is equal to the number of data. We can try one by one. Once we consider the number of clusters to be 1, we calculate the distance of the data to the center and calculate the objective function in this order. We continue this work by increasing the number of clusters by 1 unit. As the number of clusters increases, the value of the objective function becomes smaller and smaller, until the number of clusters is equal to the total number of data, and finally the objective function becomes 0. Then such a diagram can be drawn. The vertical axis is the value of the cost function and the horizontal axis is the number of clusters. You can see here that chi is optimum when the number of clusters is 3. Because before that the slope is too high, and after this point the value of the objective function will not be much different. This method is called elbow due to the shape of the diagram. We don't always end up like this. Unless, for example, the shape of the diagram does not have any angles, we must use other methods, but this method is useful in many cases. Now, if we find the local optimum solution, we should use the same sequence method for a method of dividing and merging clusters. We said that this method is called post-processing. This is the way to improve clustering. For this, we define 2 actions. One is split. For this, we have to choose the worst cluster. So we choose the cluster that has more dispersion to divide. This concept is also called the Ward criterion. We use the Cummins algorithm itself to divide into 2 clusters. We ask the algorithm to put the data in this scattered cluster into 2 separate clusters. The next step is the integration step. Here, calculate the distance of the clusters 2 by 2. Every time we divide, the number of clusters increases. This value is fixed, so we have to do this division step and integration step, merging step, actually one after the other. First, we compare the similarity of the clusters. Calculating cluster similarity has different methods. We find 2 more similar clusters and merge them together. Here we have reached the optimal solution with only 1 division and 1 merging. But in real-world examples, we need the sequence of these steps. The post-processing method has a good speed. There is another method that has better speed performance than Cummins, called Cummins 2-part algorithm. Each time we divide a cluster into 2 areas, we repeat this task times, and between these times we check which cluster was better to divide into 2 parts. That is, in which case the objective function decreases. We repeat this until the number of clusters reaches common implementations and examples have been placed for you in Python files. I again emphasize that not to ignore the Python files which I prepared for you. Pay attention to every single cell of the Python files available for you. And I again recommend you not to miss the upcoming lectures because of the very practical and important tips inside them that you can benefit from to become an expert machine learning engineer. Have a nice day.